In this video, we're going to go through the section 8 notes in chapter 1. So this is our last section of chapter 1, finally. So we are talking about a new topic here at the beginning. It is average rate of change. So I have 3 sketches here, and you can see from each of these sketches that the average rate of change is talking about the slope, but it's the slope of a secant line. So here's the first interval from 1 to 2. If they ask you for average rate of change, they're going to give you an interval. And what you're going to do is you're going to connect the dots. So connect the x values for 2 with the x value for 1, and then find the slope of that secant line. And I have the work done for you here, and you can see that that slope is 3. Now in the next interval, they've put the points a little bit closer. Now the points are 1 and 1.1. So once again, you're going to go up from the x-axis to your 1 and 1.1, and then go across to the y-axis and establish your coordinate pairs. Connect those coordinate pairs with a secant line and find that slope, and that will give you the rate of change. And one last time, we're going to do it with values that are even closer. Now they are 0.01 apart, but they're still 2 points on the function, so therefore they are connected with a secant line. So down below we have some things for you to fill in. So it says, notice that the interval in example C is blank, then the interval in either A or B. So on this line, you would write the word smaller. Okay? Then we go on to say, the sequence of answers from above suggests that as the interval gets smaller and smaller, the average rate of change tends towards, so what do you think? We go from 3 to 2.1 to 2.01. So I would say that the average rate of change tends to 2. So this concept of shrinking the interval should remind you of taking limits, because limits, the difference was h between 2 points, and as h went to 0, your secant line became a tangent line, and that's exactly what's happening now. So if they ask you for average rate of change, you're taking the slope of the secant line. As the average rate of change interval decreases to 0, that line goes from being a secant line to a tangent line, and that would measure the instantaneous rate of change of the function. So let's think about that for a second, and we're going to go to the next page. All right, I've subtly written here that the huge point to understand is that you're moving from the slope of a secant line, which measures average rate of change, to the slope of a tangent line, which measures instantaneous rate of change, and that's what we measure when we take the slope. So I have an example for you now, and in this example, we're going to first analyze the words and then discover whether we're going to use the average rate of change or the rate of change, which is our instantaneous rate of change. So example 2 says, consider the function f of x equals x squared. Calculate the rate of change. So if the word average is missing, and they just talk about rate of change, you have to know that that means that you're going to be taking the derivative of the function and evaluating it at only 1 point. Okay, that is probably the most key point I'm making in this lesson at this point. So, and I said, once again, to stress it, only one value is given, and that value is 1. They are looking for instantaneous rate of change. We're going to take the first derivative. So we're going to take our very familiar function, take the first derivative, and evaluate it where x is 1, and we report a rate of change of 2 units for every unit of time change. All right, now let's do a compare and contrast. Consider the function f of x equals x cubed. Okay, that is just the parent cubic function, and you're asked to calculate not one thing but 2 things. The first being the average rate of change of the function for the interval 1 to 3. So I said, hint, use the slope of a tangent line here. Then the next thing you're asked to do is to figure out the instantaneous rate of change at x equals 2. So pause the video and go ahead and do those two problems. Okay, what you should have gotten for those two problems were the following. So let me just see if I can make this bigger, and I can. Okay, so we're going to say for the average rate of change, I'm given the interval 3 to 1. So I'm going to take the f of 3 minus the f of 1 all over 3 minus 1. Okay, what's the f of 3? The f of 3 is when you take the original function and plug in the x value at the end of your interval. It's always easier to go from high to low, so pick the highest number first. So f of 3 would be 3 cubed, because it's a cubic function, minus 1 cubed, that's my numerator for rate of change, and 3 minus 1 is 2. So 3 cubed is 27, 27 minus 1 cubed is 1, 27 minus 1 is 26 over 2, which equals 13. Now I don't have any units here, so I'm just going to say it's 13 units per unit of time. Okay, the instantaneous rate of change, they just want us to evaluate at 2, and that's your tip-off that they're talking about the slope of the tangent line, which is the first derivative. So go ahead and get your first derivative of this very familiar function, and you would get 3x squared. You're now going to evaluate that function where x is 2, and you will get 3 times 2 squared, which should be 12. So the first one was average rate of change over an interval. The second one was instantaneous rate of change at a point. First one, just slope equation, slope of a secant line. Second one, first derivative, which is the slope of the tangent line. Okay, we're going to go into our next topic in this section, which is the physics application. We're going to talk about position functions, velocity, and acceleration on the next page. Okay, so position function, velocity, and acceleration. Another way to think of a derivative is as a rate of change, which we've said over and over again now. So the derivative of a position function describes the rate at which position changes. So can you think of a word from physics that describes the rate at which the position of an object changes? So you should think of a word, and it should be velocity. So this is velocity. Carrying this logic one step further, the rate at which and this is velocity again, so the rate at which the velocity of an object changes refers to another word in physics, acceleration. So we've now defined velocity as the first derivative of the position function and acceleration as the second derivative of the position function. So this is keenly important because once I tell you that, I'm not going to tell you again that it's the first position when you talk about velocity, that it's the first derivative rather. So I'm just going to ask you to find the velocity given this position function. So you have to know those derivatives and how they're defined. And then on the next page we'll practice using this. In example 3, I say, suppose a baseball is thrown upwards so that its height in feet is given by the position function ht equals negative 16t squared plus 128t plus 5. So t is my time in seconds, and here is the graph. Now, a couple of things to note. If you do a graph, like for one of my projects, you want to have a title, you want to have your units clearly identified on your x and y axis, and you want to have everything labeled so I know what your increments are. So that is a good graph. So now we can use that graph to talk about the next couple of questions. First, I ask you to find the velocity of the baseball 2 seconds after it is thrown. And I say, what is this asking you? Well, if you go up from 2 on the x-axis to your graph, and you put a point, and you draw a tangent line to that point, you can use that tangent line to find the velocity. So you're basically asked for the derivative of the function at 2. That is your velocity. So I explained it here. I've worked it out for you. That's my first derivative of the position function. So that's velocity. That's my velocity everywhere. So it's every single slope drawn to that curve, or every single tangent line drawn to that curve. And then I plug in the actual value of 2, and I get an answer of 64 feet per second. Now units will be important because that's going to indicate what you are measuring. So for your turn, I say, find the velocity of the baseball 3 seconds after it is thrown. So what you should do, I'm going to erase this line, is to go up and say, okay, 3 seconds. So I'm going to go up to the 3, and I'm going to draw a tangent line. That slope will measure the velocity at 3 seconds. So since it's a slope, I know I'm going to take my first derivative, which is negative 32t plus 128, and I'm going to plug in 3. So what I'm noticing is that it's not as steep as the previous section. So it's still positive, but not as steep. So I have an idea of what my answer is going to be. So h prime of t equals negative 32 times 3 plus 128. And I believe if you do the math, so this is 3 times, so that's 90, negative 96 plus 128. So I am getting 32, right, feet per second for the velocity at time equals 3. So make sure you understand that. Okay, now we're going to go to another question where instead of asking you the velocity, I tell you the velocity and ask you for the time at which that velocity occurs. So we'll do that on the next page of these notes. Alright, so now we're going to go down to A, and it says find the time when the velocity is negative 32 feet per second. So my solution, I go through my own solution first, is to set the velocity function equal to negative 32 and then solve for your t. So here's all my work. Another way of thinking about this is to go ahead and take your function, so I'm just going to like that. It's not a very good sketch, but you get the idea. And we're going to put a line in, and that line is going to be y equals, let's see, set the velocity equal, I take that back. So let's just skip what I said because it's not apropos for this particular example. Okay, let's go back to what I'm doing. So what I want to talk about is the next little piece. What if I say find the time when the velocity is 64 feet per second? So if it's 64 feet per second, I'm now going to set my velocity, which is negative 32t plus 128, equal to 64, and solve. Okay, so after you do the math, you should get time equals 2 seconds. Alright, so what I was saying about the graphic approach is this. If you graph your position function as the first derivative of the position function, so if you graph this, and that's your h prime of t, then you can do this analysis graphically by putting in your horizontal line for the velocity they give you and figuring out where they intersect, and that will give you the time that you need. So you can do this analysis graphically as well using your graphing calculator, but I've done it algebraically here for you. So the assignment is written below. You're going to do 1 to 15 odd, 18 to 30 multiples of 3 in our textbook. Check as you go to make sure that you're understanding it. But before we leave this video, I'm going to go back up and put the baseball parabola up, and we're going to talk about what kinds of questions they would ask you about velocity, because it seems very easy at the onset, but it gets very complicated very quickly. So in the last slide, we're going to go through the video of the graph once more and do some interpretation of possible questions. Okay, here's our original graphic, and this is the position function of the baseball, and I've given you your function here. Okay, questions they frequently will ask you. One famous question is, what is the velocity when the baseball hits the ground? So that seems like one question, but it is two questions. So how would you handle that? So having the graph in front of you, I can see that it hits the ground at 8 seconds. If I didn't have a graph in front of me and I only had the function, my first step would be to find the roots. And you're finding the roots of the parabola, so you're going to do that by factoring or by quadratic formula and getting the x value. At that x value, and we'll call that x value t ground, that's the time it hits the ground, that is going to help you get your velocity, because then your second step is going to be to take the velocity function, which is the first derivative of the position function, and evaluate it at tg. That will give you the velocity where the ball hits the ground. Now, just a little note, when you find the roots of a parabola, you're going to get two roots. One is the root you need, and one is an extraneous root that you don't need. So you're going to have to recognize that and know that you're going to throw out the extraneous root and only evaluate the root that gives you the perspective that you want. Okay, a second popular question is, where is the velocity 0? So it's not where it hits the ground. The velocity is 0 where the slope of the tangent line drawn to this curve is 0, and that's going to be at the max. So how do you know the max? Well, you can set the velocity equal to 0 and solve for your t, so that will give you the t that you need. Or you can remember from Algebra 2 that because it's the vertex, you can get the time by using your quadratic equation and just saying negative b over 2a. They frequently will ask you what the height is at the greatest path. So it's pretty easy when you have a graph, but when you don't have a graph, you're going to have to take that t value and plug it where? Plug it back into your original equation. Or you can take your function and evaluate it at that t value, identified as negative b over 2a. So these are the kind of questions that you should be prepared to reflect on for this section. Additionally, you should be able to tell me where the velocity is positive, and that's going to be all here as your function is increasing. It's 0 at the top, and then your velocity turns negative here. A second question they frequently will throw out is about the acceleration. So you've got to know acceleration is going to be the second derivative. So what will acceleration be? Well, it looks to me like it's going to be negative 32. So it's up to you to verify that. And since it's just negative 32, your acceleration for a parabola type function is always going to be a constant. So it's going to be time independent. So anyway, I've given you some things to think about. So make sure you have good notes for this section and then tackle those problems.